Page 119. Product and quotient rules and higher order derivatives. Product rule and quotient rule for today. So up until now, the only things we can find derivatives of without using the definition are basically polynomials, right? And sine and cosine. If we had two quantities multiplied together, or a quantity divided by another quantity, unless we could rewrite it so that we could use the combination rule or one of our trig rules or the constant multiple rule, then we had to use the definition. But now we're going to greatly expand the number and types of functions that we can take the derivative of by using rules. Now, we call them rules. Everybody calls them rules. They're actually theorems that have been proven to be true. Okay? So here's what the product rule says. The product of two differentiable functions, f and g, is itself differentiable. In fact, that's true if there's 3 differentiable functions or 74 differentiable functions. As long as all the functions you're talking about are differentiable, the product of them is also differentiable. Moreover, the derivative of f times g is the first function times the derivative of the second plus the second function times the derivative of the first. And that's really the way I have it memorized. First function times the derivative of the second plus the second function times the derivative of the first. Because I think that the words are as easy to memorize as the symbols. I think the symbols are kind of complicated to memorize. This means the derivative with respect to x of f of x times g of x equals f of x times g prime of x plus g of x times f prime of x. So the first function times the derivative of the second plus the second function times the derivative of the first, that's the product rule. If you are going to try to memorize it in symbols, I'd leave out the x's. I would write it like f times g prime plus g times f prime. I think that makes it a little easier to memorize without all the x's. And let's work an example. Now, even though we know the product rule now, quite often it would be just as simple, if not simpler, to multiply everything out first and then do what we've been doing using the combination rule after that. But we're going to complicate it up as we go, okay? So this one here that I'm going to do as an example, it would probably be just as it'd probably be easier, as a matter of fact, to just multiply that all out first, then take the derivative of each term. But I tried to come up with one that was easy enough for you to follow, okay? So here we go using the product rule. So h of x equals x squared minus 3 times 4x cubed minus 3x plus 1. So the first parentheses will be your first function. The second parentheses will be your second function. So f is x squared minus 3. G is 4x cubed minus 3x plus 1. So according to the product rule, the derivative of that, which we can call h prime, equals the first function, so the first parentheses, x squared minus 3, times the derivative of the second function. So we actually got to do some calculus this step. So what's the derivative of 4x cubed? 12x squared, using the combination rule. Exponent times coefficient to get the 12, then your x, then subtract 1 from the exponent, so 12x squared. What's the derivative of negative 3x? Negative 3, what's the derivative of 1? 0. So we've got the first function times the derivative of the second function. Plus the second function 4x cubed minus 3x plus 1 times the derivative of the first function. Well, what's the derivative of x squared? 2x. What's the derivative of negative 3? 0. That's the one step of calculus. The rest is going to be simplifying. The rest is algebra. Okay, so y'all with me on using the product rule? First function times the derivative of the second plus the second function times the derivative of the first. All right, now we got, see, and here's why it probably would have been easier just go ahead and multiply it all out first, because we still got a lot of multiplying to do, don't we? So we use the FOIL method here. X squared times 12x squared is 12x to the fourth. And then x squared times negative 3 is negative 3x squared. Negative 3 times 12x squared is negative 48x squared. And negative 3 times negative 3 is 9. So all of that comes from multiplying those two parentheses together, these two quantities here. Copy down the plus sign. And then here, I just need to distribute the 2x, don't I? Yes. What did I say? That looks like a 48 to you? What kind of math symbols are you using? So, when we combine like terms, we'll get 20x to the fourth, and we won't get negative 57x squared. We'll get negative 45x squared plus 2x plus 9. I think it's right. Isn't it right now? Okay. All right, now, we're going to use the product rule all year. So you might as well learn it now. Don't lose points on the next quiz thinking, it's just one quiz. No, you will lose points from here on out. It will be on every single quiz, every single test from here on out in some form or fashion. Maybe there's an exception or two, but I mean, you got to know it. Okay? Questions? Yep. That's the derivative. That's the formula to find the slope of the tangent line of that function. That's 2x. 2x times 1. All right. Quotient rule. You thought the product rule was fun. You haven't seen anything yet. Because the quotient rule is awesomer. Not for a while. Yeah, I mean, this will do you for a while. The quotient, f divided by g, of two differentiable functions, f and g, is itself differentiable at all values of x for which g of x does not equal 0. So if you have two differentiable functions, the quotient of those two differentiable functions is also differentiable, with the exception of making sure that the derivative does not equal 0. Okay? So some denominators will have x coordinates that make them equal 0. Well, the derivative does not exist at those x coordinates. Okay? Moreover, the derivative of f divided by g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. That's not the way I have it memorized. I have it memorized like this. the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's the way I have it memorized. Okay? The top times the derivative of the bottom minus the bottom times the derivative of the top over the bottom squared. One more time. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now, I had somebody years and years ago describe it to me in what I thought was a silly way. And so I would always tell my students this silly way so that we could laugh at this silly way. Turns out students really like this. So let's see if you do. Low-D high minus high-D low over low-low. Do you see what they're talking about? Low, the bottom, D high, derivative of the top, minus high, D low, over low-low, low. Whatever works, you got to memorize it. Okay? So if low-D high minus high-D low over low-low works for you, then great. Or if the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared works for you, great. If the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator, works for you, go for it. If you're going to use symbols, I would do it this way. I'd do that for the bottom, that for the derivative of the top, minus that for the top, that for the derivative of the bottom, over, and then that for the bottom squared. All right, so let's do an example. We have y equals 3x squared over the quantity 3x plus 2. And we just flat out wouldn't be able to work this without. Okay, we could not have done this one 30 minutes ago, right? So here's what we do. So the derivative, y prime, equals the bottom, 3x plus 2, times the derivative of the top. What's the derivative of 3x squared? 6x, using the combination rule, minus the top, 3x squared, times the derivative of the bottom. What's the derivative of the bottom? 3 over the bottom squared. All right, so there's our one step of calculus. The rest of this is going to be algebra. So any questions on the calculus? All right, good news is the denominator's in pretty good shape, right? A quantity with an exponent on it, that's usually simplified. Usually, okay? So, in the numerator, multiply the things together in front of your minus sign, so distribute that 6x. 6x times 3x is 18x squared. 6x times 2 is 12x. Then you copy down your minus sign, and then you multiply 3x squared times 3 to get negative 9x squared. Well, minus sign, 9x squared. And then leave your denominator alone, 3x plus 2, quantity squared. We can keep simplifying in the numerator. We can combine 18x squared and negative 9x squared to get positive 9x squared plus 12x over our denominator squared. it's a good idea to factor. At this point, I will not require you to. Eventually, I will require you to. So we can factor out a 3x, can't we? So take out a 3x from the numerator. Well, 9x squared divided by 3x is 3x. And 12x divided by 3x is 4. And leave the denominator alone. Sometimes a nice thing happens at that point, and sometimes you can divide out a common factor from the numerator and denominator. Sometimes. And that's the quotient rule. All right, questions? All right. We need the derivatives of the other trig functions. The derivative of the tangent of x equals secant squared of x. And remember what that means? Students get this messed up sometimes. Secant squared of x means the secant of x with the parentheses around it squared. All right, so they just over the years developed a notation to eliminate the parentheses. Okay, so that's how they do it. Secant squared of x means secant of x, taken as a quantity, squared. Then the derivative of the cotangent of x is negative cosecant squared of x. The derivative of the secant of x is fun. That's secant of x times the tangent of x. And the derivative of the cosecant of x, equally fun, negative cosecant of x times cotangent of x. Notice that the derivatives of the cos are negative. The derivative of cosine was negative sine of x. The derivative of cotangent is negative cosecant squared of x. The derivative of cosecant is negative cosecant of x, cotangent of x. So it's the cos whose derivatives are negative. The other ones, not. All right, let's do this example. F of x equals the tangent of x minus the cotangent of x plus the secant of x plus the cosecant of x. Isn't that amazing? I was able to work all four of those into one problem. Ooh. All right, so f prime of x equals, all right, take the derivatives one term at a time. What's the derivative of the tangent of x? Secant squared of x minus, why minus? Because it was in the problem I made up. Now, what's the derivative of the cotangent of x? Negative cosecant squared of x. So another negative sign than a cosecant squared of x. Plus, what's the derivative of the secant of x? Secant of x times the tangent of x. Plus, what's the derivative of the cosecant of x? Negative cosecant of x, cotangent of x. All right. I don't like minus negative, so let's make that secant squared of x plus cosecant squared of x. Nothing to do to the plus secant x, tangent x. And then instead of plus negative, let's just go with minus the cosecant of x times the cotangent of x. And we'll call it good. And now let's work some examples from the book. Page 126, number 12. Use the quotient rule to differentiate the function. All right, we're going to use the quotient rule. So if f of t equals the cosine of t over t cubed, that is a quotient made up of two differentiable functions. Okay? So f prime of t will equal the bottom, t cubed, minus the derivative of the top. What's the derivative of the cosine of t? I said minus, times the derivative of the top. What's the cosine of t? Negative sine of t, minus the top, cosine of t, times the derivative of the bottom. What's the derivative of t cubed? 3t squared. Over bottom squared. It's going to be t to the 6th. All right. Simplify in front of your minus sign. Let's make that negative t cubed sine of t. And it's more common to see the 3t squared written in front of the cosine than not, right? So keep the minus sign and then rewrite that as 3t squared minus the cosine of t. Why do I keep saying minus? Times the cosine of t. Over t to the 6th. Is there a greatest common factor I can divide or factor out of the numerator? T squared. Should I take out the negative as well? Who knows, right? Sometimes it turns out you need to. Sometimes it turns out you don't. So I won't yet. Maybe I'll need to. I'm not going to yet. It's not wrong if I do. Okay? I'm just not going to yet. So I can take out a t squared. And when I divide out a t squared, negative t cubed sine of t divided by t squared gives me negative t sine of t. And then negative 3t squared cosine of t divided by t squared gives me negative 3 cosine of t. T to the 6th in the bottom. Should we? And I'll stop there. Now, if we had taken out the negative, and you need to recognize that those are equivalent answers. Okay? So if you may check in the back of the book, and you may have one version and they have the other, well, you got it right. Okay? Questions on 12? Let's try 13. In exercises 13 through 18, find f prime of x and f prime of c. So they're trying to remind us here that when we're finding derivatives, we're actually finding something to be used. Every time we find a derivative, no matter how simple it is, no matter how complicated it is, we're finding a formula to get the slope of the tangent line, a formula for the rate of change, a formula for the velocity of a moving object. So they're trying to remind us of that. We're going to find the derivative, and then we're going to use that as a formula for when the x-coordinate equals 0 in this case. Okay? All right, so f of x equals x cubed minus 3x times the quantity 2x squared plus 3x plus 5. Let's practice the product rule. Once you've convinced me you're good at it and you'll never mess it up, I might tell you to go ahead and multiply that out first. It's one of those 6 of one thing, half a dozen of the other, or as somebody once said, 6 of one thing, 7 of the other. I'm like, no, that's not the saying. All right, so let's product rule it. So we're going to have f prime of x equals the first function, x cubed minus 3x, times the derivative of the second function. What is the derivative of the second function? 4x plus 3. Plus the second function, 2x squared plus 3x plus 5, times the derivative of the first. What is the derivative of the first?
3x.
All right, so we've done our one step of calculus. Now multiply. You got it. So x cubed times 4x is 4x to the fourth. X cubed times 3 is 3x squared. Negative 3x times 4x is negative 12x squared. Negative 3x times 3 is negative 9x. So that takes care of the first multiplication. Now to do the second one. First, distribute the 3x squared. So 3x squared times 2x squared is 6x to the fourth. 3x squared times 3x is 9x cubed. And 3x squared times 5 is 15x squared. So that takes care of distributing the 3x squared. And we've still got to distribute the negative 3. Negative 3 times 2x squared is negative 6x squared. Negative 3 times 3x is negative 9x. And negative 3 times 5 is negative 15. Combine like terms. How many x to the fourths do we have? We have two different terms, and when you combine them, 10x to the fourth. All right, what do we end up with? What x cubed? What's the coefficient on x cubed? 12. And the coefficient on the x squared? What kind of 3? Why would it be positive? We have that one and that one. All right, don't we have those 3? All right, so negative 3x squared. All right, what x? And what's our constant? And that is our formula to find the slope of the tangent line, the rate of change, the velocity of a moving object. The prime of f of x is what? Uh-huh. No. What we have is f prime of x. To get f prime of c, we use the value of c they gave us. So in other words, they're now saying find f prime of 0. Well, that's good. Using a 0 is good. If they'd said find f prime of 17, that'd be a little more work, because we'd have to raise it to the fourth, then times 10, and so forth. Okay? So f prime of c, which in our case, since c equals 0, is f prime of 0. Well, 0, 0, 0, 0. Only thing left is negative 15. So we found the formula, we used it. Number 30. Now the directions say to find the derivative of the algebraic function. Our f of x equals the cube root of x times the quantity, the square root of x, plus 3. All right, I'm going to show you two different ways to work this one. Okay? The first way we're going to do it is we're going to product rule it. But before we can product rule it, is to find the derivatives of radicals, we have to write the radicals in exponential form because we have a power rule and a combination rule that handles x with an exponent on it. We don't have any rule that handles a cube root of something, and we're not going to have a rule. Okay? So let's rewrite those in exponential form. So I haven't done any derivative. I've just rewritten the cube root of x as x to the 1/3, and the square root of x is x to the 1/2. And now, let's product rule it. So this will be f prime of x equals the first function, x to the 1/3, times the derivative of the second function. What's the derivative of x to the 1/2? 1/2 x to the negative 1/2. What's the derivative of 3? Okay. So that's the first half of the product rule. The first function times the derivative of the second function. Plus the second function, x to the 1/2 plus 3, times the derivative of the first function. What's the derivative of x to the 1/3? 1/3 x to the negative 2/3. 1/3 minus 1 is negative 2/3. All right, so we've done our calculus. All right, now, what we got to do now is we need to multiply. And here's where it gets a little sticky, right? Because when we multiply factors with the same base, the x to the 1/3 has a base of x, the x to the negative 1/2 has a base of x. When we multiply factors with the same base, what do we do to the exponents? Add them. And since the exponents are fractions, what must we do with those exponents so that we can add them? Get a common denominator. All right, so I've got a coefficient of 1/2. Now, those x's, what's the least common denominator if our denominator is 3 or 3 and 2? 6. So x to the 1/3 can be thought of as x to the 2/6. And x to the negative 1/2 will be x to the negative 3/6. So I'll actually do the multiplication next step. I got it set up so far. Okay. Now, on the other side of my plus sign, I need to distribute that 1/3 x to the negative 2/3, and I need a common denominator if I'm going to add the exponents. So distribute the 1/3, and then the x to the negative 2/3 and the x to the 1/2. Write the x to the 1/2 as x to the 3/6. Write the x to the negative 2/3 as x to the negative 4/6. Plus, right, I'm going to actually write it out, but you're right, we're going to get x to the negative 2/3. I'm going to write out 3 times 1/3 x to the negative 2/3. Eventually we're going to have to, aren't we? All right, all the way over to the left. 1/2. What's x to the 2/6 times x to the negative 3/6? That's right. When you multiply factors with the same base, add the exponents, so we get a negative 1/6. Plus 1/3 x to the negative 1/6 plus, and I'm still writing this as x to the negative 2/3, but is that negative 2/3 going to hold up for the whole problem? Yeah, we'll see. All right, so what do we get next? Well, these two terms are actually like terms. So we can combine their coefficients. Now this, let's do in our head. 1/2 plus 1/3, that'd be 3/6 plus 2/6, 5/6, x to the negative 1/6, plus x to the negative 2/3. And I just got rid of the negative exponents and called it a day. Should I have? For now, let's just do this. So I kind of wimped out a step away or 2 steps away from getting a little bit better answer, but we're okay for now. All right, did you follow all that? So using the product rule led us to some fairly, difficult's not the right word, annoying simplifications. Okay? So let's try it in a different order this time. Let's redo it. We've got f of x equals the cube root of x times the quantity, the square root of x plus 3. Let's go ahead and rewrite this in exponential form. But instead of using the product rule, I wonder how this is going to work out if I just multiply that out first. So let's do the annoying rewriting first instead of last. So what's x to the 1/3 times x to the 1/2? Oh, that common denominator thing again. So what's my common denominator going to be? So let's make that x to the 2/6 times, and then inside the parentheses, let's make that x to the 3/6 plus 3. Now let's distribute that x to the 2/6. When I multiply x to the 2/6 times x to the 3/6, I get x to the 5/6. And then I realize at this point I'm not going to get the same looking answers I had the first time because I left this one term with the denominator of 3. So I kind of backed off and made that one, instead of 3x to the 2/6, I made it a 3x to the 1/3, only because I'm going to try to make my answers look the same. Okay? I really want my answers to look the same, because that way I'll know I've done it either way works. All right, we still haven't done the calculus. Now take the derivative. So what's the derivative of x to the 5/6? 5/6, x to the negative 1/6. Then we take the derivative of 3x to the 1/3 using the combination rule. And we get the same thing when we're through simplifying. So like I said, sometimes, even though we've learned the product rule, sometimes it's not really the best way to go about it. Yeah. Good question. You will get more of a feel for it, especially when, after you've done the product rule and you still have a lot of multiplying to do, at that point you might back up and say, why don't I just do the multiplying first and then take the derivative of each term at the last? And, it really is, it's just an experience thing. And even I've been doing this for 100 years, and sometimes I would work it one way and realize when I'm done, or maybe well, actually a couple of steps in, and I kind of wish I'd have multiplied it out first. But I'm also kind of stubborn, and once I've started it one way, I'm going to try to finish it that way if I can. All right? Another one, 34. Find the derivative of the algebraic function. So we've got g of x equals x squared times the quantity 2 over x minus 1 over x plus 1. I'm going to distribute that x squared through there. Okay? So I'm going to multiply x squared times 2 over x. What do I get? 2x. And then minus sign. And then x squared times 1 over x plus 1 is just x squared over x plus 1. Don't lose your minus sign. And now look what we have. To take the derivative of 2x is a piece of cake, right? Then we'll copy down the minus sign, and then we'll use the quotient rule to get the derivative of that. So, g prime of x equals. Now the derivative of 2x is 2. Copy down the minus sign. Everybody can get 2 minus, right? All right, 2 minus, and then quotient rule it. Low-y high minus high-y low over low-low. So the bottom, x plus 1, times the derivative of the top, 2x, minus the top, x squared, times the derivative of the bottom, 1, over the bottom, squared. So we've got 2 minus. All right, let's distribute the 2x. 2x times x is 2x squared. 2x times 1 is 2x. And then negative x squared times 1 is negative x squared. Denominator doesn't change on this step. So we have 2, leave some space, minus. And then 2x squared and negative 2x squared give us x squared plus 2x over x plus 1 quantity squared. All right, now, we were wimps on the one we did before because I was just so grateful that you could follow me on the changing the radical to an exponent, getting a common denominator with the exponents. We didn't bother getting it as one final big, huge quotient. Well, we are now. So, if this term has a denominator of x plus 1 quantity squared, and we're going to combine that 2 with it, don't we have to turn that 2 into a term that has a denominator of x plus 1 quantity squared? How do we make equivalent fractions? Multiply by the denominator you want over itself, right? So we multiply by x plus 1 quantity squared over x plus 1 quantity squared. So we know what the denominator is going to be. It's x plus 1 quantity squared. But in the numerator, now, x plus 1 quantity squared, that's a plus b quantity squared. You get a squared plus 2ab plus b squared. So we've got 2 in front, and then we get a squared plus 2ab plus b squared. Minus, now let's distribute that negative. This negative right here, let's distribute it. Let's make that minus x squared minus 2x. Almost done. 2 more steps. Distribute the 2. 2x squared plus 4x plus 2. Everything else just gets copied down. And combine like terms. When you combine like terms, what's your numerator now? X squared plus 2x plus 2. Well, that was fun. Come on, that was fun. It's a short assignment. Doesn't take up much space on the screen. Do what?